Hi, this is Chris and Kevin with the Locomotor Control Systems Laboratory at the University of Michigan. Today we're here to talk to you about some of the features and technological advancements of our lab's second-generation knee-ankle powered prosthesis.
This prosthesis is instrumented with a thigh-mounted IMU, which is used to compute the phase variable in many of our lab's controllers. Frameless knee and ankle motors are built into a custom-designed housing with 22-to-1 stepped planetary gear sets. This quasi-direct drive architecture allows for excellent backdrivability, which we'll be demonstrating shortly. This backdrivability presents a lot of advantages, including open-loop torque control, regenerative braking, reduced audible noise due to power transmission, and a greater compliance during impact events, which results in a more comfortable user experience.
Another interesting aspect of this design is the 4-bar linkage that we use to transmit torque from the ankle motor down to the foot. While this linkage doesn't amplify any torque, what it does is allow us to locate the ankle motor more on the proximal end of the shank. This reduces the inertial effects of the motor felt at the knee and the torque required to accelerate the shank. This reduces the loads applied at the socket and overall creates a more comfortable experience for the user. Lastly, a 6-axis load cell on the foot measures ground reaction forces and moments. This gives us real-time kinetic information and ground contact information that we can use in our controllers.
In this example, Kevin is going to demonstrate the backdrivability of the ankle and knee joints. Earlier results from similar benchtop tests revealed that the peak torque required to backdrive the actuator was around 3 Newton-meters. Similarly, previous benchtop tests have shown that the knee is capable of swinging from 65 degrees all the way to full extension in about half of a second. This means that much of the swing phase dynamics can be completed in a completely passive manner.
Another consequence of this high backdrivability and minimal unmodeled actuator dynamics is the system can perform open-loop torque control. As I'm demonstrating this video, we can get accurate impedance behavior without the addition of any load-side sensors. This has significant implications for both cost and weight savings in designs that use this actuation paradigm. In a previous study, we characterized the open-loop torque control performance by measuring the actual output torque at the load. As you can see in the plots, the tracking was very accurate at the torque values seen in walking. For more information, see the paper linked in the description.
While this leg is capable of accurate impedance control, its high torque motors also work well for position control paradigms. In this example, Kevin will command the leg to track a sine wave at a frequency similar to what would be required for fast walking. Since there are no elastic elements in the drivetrain, the position can be accurately tracked. As these plots show, the leg is capable of tracking human gait trajectories at a variety of speeds with high accuracy. Previous benchtop tests found the cutoff frequency of the system to be over 10 Hz for input commands up to 15 degrees, which is significantly above the frequencies required for running. Now we're going to cut to a treadmill demonstration in which Kevin walks on the leg with a bypass adapter.
Alright, now we'll show one of the controllers that we've implemented on this leg and some of its notable features. The treadmill footage you're about to see is actually my first day doing treadmill walking on this prosthesis. You may notice some compensatory behavior or slight stumbles as I got used to the bypass adapter and the shoe lift on the contralateral leg. However, this highlights one of the benefits of this controller. Its intuitive user control interface allowed me to acclimate to using the device with minimal training time.
This video shows Kevin using our holonomic phase-based controller from the paper indicated on screen and linked in the description to walk at 1.2 meters per second. You may notice that he occasionally leaves the prosthesis suspended in late swing before heel strike. While this was more of a result of his acclimation to the leg than an intentional demonstration, it does show that our controller is capable of accommodating asynchronous gait actions like this, which would not be possible on a purely time-based controller.
In addition, we want to take a moment and highlight a few more of the design features of this prosthesis. First, all electronics and power source and associated components for the leg can be self-contained. All computation is done on board the MyRio, which is mounted on the front of the device. In practice, the lithium-ion batteries that we use to power it can also be mounted to the pylon between the knee and the ankle motor. However, in this demo, we have them mounted on the waist for convenience of swapping out batteries. Lastly, we would like to point out the low acoustic noise from the prosthesis. Mainly what you hear during this demo is the bypass adapter creaking, impacted heel strike, and sounds of the treadmill system. If you listen very closely during swing, you can faintly hear the transmission noise. This is an important feature for prospective users who may have a preference for a quiet prosthesis. This setup would allow them to participate in community ambulation without drawing potentially unwanted attention.
The benefit of using the thigh angle as a phase variable is that it allows us to implement backward walking with a relatively simple set of modifications. In this next video, Kevin demonstrates the ability to smoothly transition between forward and backward steps in overground walking using only the information conveyed by thigh motion.
Thanks for taking the time to check out this demonstration of our lab's highly back-drivable knee-ankle powered prosthesis and our associated control systems work. We would like to thank the members of our lab for all their hard work and for our funding agencies for making this work possible.
If you're interested in learning more about this or other hardware and controllers that our lab is working on, we suggest you attend Dr. Gregg's IROS2020 talk. We hope you enjoy the rest of this workshop and IROS as a whole, and that you reach out to our team if you have any questions or related topics you would like to discuss.